Dear students, welcome to the fourth lecture of Unit 3, Advanced Control Systems. Today we are going to talk about a concept called duality. Please remember that in the last lecture we talked about observers and observer design. Briefly, we saw that the aerodynamics after you incorporate an observer into the system in order to estimate the states of the system, so that you are able to implement a control law given by u is equal to minus kx cap, where x cap is an estimate of x. In order to have this estimate, you implement an observer which has aerodynamics given by x tilde dot is equal to a minus mc x tilde, where x tilde is the error between x and the estimate of x, and the observer equation is given by x hat dot is equal to ax hat plus bu plus m y minus y hat. So here what you're basically doing is you're implementing a Leuenberger observer given by this equation, and in implementing this observer ensures that your aerodynamics are given by this. So you're basically arbitrarily able to place the poles of your aerodynamics, and you can ensure that your aerodynamics is very fast and the error becomes zero very fast. And when the error becomes zero very fast, so your x tilde tends to zero very fast, that means your x cap will tend to x very fast, and because of this your control law u is equal to minus kx cap would be a good equivalent of the actual control law which you wanted to implement, which was u is equal to minus kx. So as is evident from this, what you're doing is basically again something very similar to what you did when you arbitrarily placed the poles of a plant using u is equal to minus kx only. That is, you are basically controlling the eigenvalues. You are placing the eigenvalues of a minus mc. Your choice of m, which is going to be a long n cross 1 matrix for a seesaw system, is such that a is equal to m minus mc eigenvalues are arbitrarily placed. So in a way, when you're told to design an observer, you'll be basically told to design an observer which has aerodynamics on such and such, which has such and such aerodynamics, that the aerodynamics have poles at this point and this point. So when you do this a minus mc, there is a similarity to the control law that we have been implementing before. Now see, when you say that a minus mc eigenvalues are arbitrarily placed, what you're saying is that the determinant of si minus a minus mc is in your control, because you have control over m. And when you say the determinant of si minus a minus mc is in your control, since si minus a minus mc, if you take the transpose, you must be knowing that when you take the transpose of matrices like this, you can individually transpose the terms. So you have si transpose minus a minus mc transpose. You can take the transpose n, and again you can take it in, and here si transpose, because it's a diagonal matrix, is si only, minus you can take this a transpose n, and the transpose of mc transpose is c transpose m transpose. And we already know that the determinant of a, some matrix A, is equal to the determinant of the transpose of the matrix. So this implies that determinant of Si minus A minus MC is equal to the determinant of Si minus A transpose minus C transpose M transpose. So what does this equation imply? This equation implies that when you're placing the poles of A minus MC arbitrarily, when you're doing this placement arbitrarily, you are actually also placing the poles of the matrix A transpose minus C transpose M transpose. And look at the resemblance of this equation with the equation for controller design, which was A minus BK. So you have A and A transpose. These are system properties. C transpose and B, this is again a system property. And then you have these matrices M and K, which are in your control. From this, what actually implies is that if you have a system called the dual system or the auxiliary system, dual or auxiliary system, whose A is the A transpose and whose B is the C transpose of the actual system, and you're able to do control design for this system such that you're able to place the poles of the plant arbitrarily, then you have actually done the observer design for your original system. So I'll write this more clearly. Suppose you have a system which is the dual or the auxiliary of the original system. Your original system is x dot, or the plant is ax plus bu. We are talking about this throughout. Y is equal to cx, and you are basically trying to design an observer for this, and the control law which you would actually implement on this would be u is equal to minus kx. So the dual system or the dual problem would be z dot is equal to A transpose Z plus C transpose U. And the control law that you will be using, you will be implementing on this would be U is equal to minus M transpose Z. So for this dual system, when you are placing the poles arbitrarily using this control law, what you are doing is you are placing the poles of A transpose minus C transpose M transpose. You are placing these eigenvalues arbitrarily. Just like when you did the pole placement for this, what you were doing was that you were placing the poles of A minus BK arbitrarily. See the similarity? This is A, this is A transpose, this is B, this is C transpose, this is K, this is M transpose, and these two equations are similar. So in a nutshell, when you are arbitrarily placing the poles for this control law applied on this plant, which is an imaginary plant that you have created from the actual plant, what you're doing is in effect arbitrarily placing the poles of A transpose minus C transpose M transpose. This automatically ensures that your actual objective of arbitrarily placing the poles of A minus MC is met, because placing the poles of A minus MC is equivalent to placing the poles of A transpose minus C transpose M transpose. So in a way, when we say design an observer for a system, so the problem design an observer for a system x dot is equal to ax plus bu, y is equal to cx, such that the eigenvalues of a minus mc are placed at such and such location where the observer equation is x cap dot is equal to ax cap plus bu plus m y minus phi cap. This problem is automatically converted into a dual problem, which is design a controller, or you can say a state feedback controller for an auxiliary system with A equal to A transpose, A matrix equal to A transpose, B matrix equal to C transpose, such that the eigenvalues of A minus A transpose minus C transpose M transpose are placed at such and such location where the controller state feedback matrix K is equal to M transpose. So by converting this observer design problem to a controller design problem, what is useful is that all the methods that you've applied for control design, for state feedback control design, can be applied for observer design. So you have to design the observer for the dual system, and then automatically the matrix that you get, which would be M transpose, has to be transposed to get the M for the original system. And this is totally logical, because if the basic criteria for control design, state feedback based control design, is your system is controllable. If your system is controllable, it automatically ensures that your dual system is observable, because controllability means b, ab, a square b, a to the power n minus 1b has rank n for a CISO system. And in this case, the dual system, the B matrix is C transpose, the A matrix is A transpose, C transpose. So just replace the A and B matrices for the dual system. So this goes on A to the power n minus 1 C transpose. So this would have a rank n, and when this has a rank n, because how would this have a rank n? Because we have already seen that if a system is observable, then you can straight away design the observer for it. And now your dual system has this as the controllability matrix, and this has rank n because the original system is observable. You set out to design the observer for it, so it was observable. and it automatically ensures, it automatically comes from the fact that the original system has the observable matrix because this matrix is equal to C CA C transpose A CA whole square and goes up to CA to the power n minus 1, transpose of this. So this matrix is equivalent to this. So this would have a rank n because the original system is observable. And since the original system is observable, the dual is controllable. And you can see that the dual is controllable because by transposing the original system's observability matrix, you get the controllability matrix of the dual system. So when you set out to design an observer for an observable system, the controllability matrix for the dual system is also of rank n, so you can design the controller for the dual system, and automatically it ensures that you are able to design the observer by designing the controller for the dual system. In order to fully comprehend what we have done in the last few lectures, I would suggest that you see some solved examples from the book. Because the examples are given in the book, it is not necessary for me to repeat them here. It would unnecessarily increase the amount of time that we spend on these video lectures. So kindly see the solved examples 7.1, 7.2, 7.3, 7.4 from the book of M. Gopal, which I have already recommended for this course. Thanks a lot for watching.